Okay, today we're talking about Chapter 6, Section 2, Rational Exponents. So we're building on the last section where we talked about radicals. We're now going to be taking these radicals and also looking at them with rational exponents. Rational exponents create radicals, and we'll see that here in a moment. Alright, so we'll do it this way. Alright, so starting from the top here, we have the definition of 1 over n, the definition of a raised to the 1 over n power, and a raised to the m over n power. So in this section, the properties, again right here, the properties for simplifying expressions with integer exponents are expanded to include expressions with rational exponents. We begin by defining the expression of the form a to the 1 over n. So here's our definition. If we're going to let a be a real number and let n be an integer such that n is greater than 1, if we have the nth root of a is a real number, then a to the 1 over n is equal to the nth root of a. So notice how the denominator of the exponent and the denominator of the rational exponent is the root. Okay, so we can write this. So this particular problem, we have negative 8 raised to the 1/3, so that we have the denominator here is a 3, so we can say the cube root, let's put it in white actually. So a, we would say the cube root of negative 8. And that's it. And then b, we see that we have 81 raised to the 1/4 power, so that 4 becomes the root. We put 81 there. C, we have the negative 100, negative 100 raised to the 1/2 power. Okay, well, notice how, first of all, notice how C and D are different, right? So C can be written like this, negative 1 times 100 raised to 1/2 power. Okay, so we can write it like that, and then we have the 100 raised to 1/2 power, so we know that is going to be just simply equal to, actually let's keep that there. So we have negative 1 times the square root of 100. Okay, well, we don't put the 2 there because again it is an implied 2, right? Let's fix that radical up a little bit. So we have 100. Well, we know what the square root of 100 is, that's 10. So negative 1 times 10 is just equal to a negative 10. D, now D is a little different because now we can't separate the negative 1 from the 100. So this is just simply saying the square root of, negative 100, right? Because it is a 1/2 power, so we would just simply say the square root of negative 100, which we know is not a real number. And then E, well, heck, E is, well, no, it's not, never mind. All right, so E is 16 raised to the negative 1/2 power. Okay, well, we learned from previously, if we have a negative exponent, then we can rewrite that as 1 over 16 raised to the 1/2 power. And then we know the 1/2 power is the square root of, the square root, so we would say the square root of 16, and then therefore 1 over the square root of 16, which is a 4, so 1/4. Right. So let's expand on this definition and talk about m over n. Okay, so on example 1, the m was simply a 1, right? That's what we did with the definition here. The m, where are we at? So we have a to the 1 over n, the m being the numerator of the exponent, and now we're going to be talking about a more broad example. And honestly, this might be the one that should have been led with, to be honest. I hope it just goes to E. Let's see. Let's make a double sure here. Okay, good. We just go to E. Alrighty, so looking at from the top here, if we have the nth root of A is some real number, then we can define an expression of the form a raised to the m over n power in such a way that the multiplication property of exponents still holds true. So, for example, the definition of a to the m over n power. Let a be a real number, and let m and n be positive integers such that m and n share no common factors, and n is greater than 1. If n... did something get chopped off there? Huh. It did get chopped off there. Interesting. Okay, so so it just says then and then and it quits. So instead what we're going to do is we are going to make this definition ourselves. Okay, so that's unfortunate. If we have, and we'll just do it this way, we'll just make this whole page, a to the, let's do m over n, okay? That is equal to the nth root of a raised to the m power, or, well, I guess I could, let's bring that down just a tad. Let's put it right here. There we go. All right. Or it's equal to, I say or, and it's also equal to the nth root, okay, that stays the same, of a all raised to the m power. Okay, so that's what that was trying to say, but it very inconveniently cut itself off. So let's try this. Let's move this to the top and put the example beneath it. Maybe that might be helpful. We also had a typo on the previous section too, so that kind of sucks. Alrighty, so let's put this in a box all by itself up here. There we go. Alright, so A wants it says, example 2 reads, convert each expression to a radical form and simplify. Okay, so in order to convert this to a radical form, we know that we can rewrite this as the cube root of 8, and then we're going to just do it this way, squared. We're going to do it the second way. The second way being this particular way. Okay, so what is the cube root of 8? Well, that's 2. What is 2 squared? Well, that's 4. So it's just going to be 4. B, we have, so again, we have a 100 raised to the 5/2 power. Okay, so this is just simply saying, what is the square root of 100 raised to the 5th power? Okay, so we would write, I'm going to do it again, I'm going to do the square root of 100, and then all that raised to the 5th power, so that's going to be equal to 5 zeros, we got 100,000, 100,000. C, 4 raised to the negative 3/2. So what we're going to do here is we're going to go ahead and put this in the denominator. So we're going to have 1 over 4 raised to the 3, small 3's. I can't write small 3's in here for some reason. 3/2. Okay. Well, this is going to turn into 1 over, it's going to be the square root of 4 cubed. So we would say the square root of 4, let's do it, square root of 4, and then cubed. Okay, well, what is the square root of 4? Well, that's 2. 2 cubed is 8, so it's just going to be 1 over 8. And let's go ahead and do E on the next page. Let's do E, which is negative 81 to 3/4 power. Oh, well, I guess I probably shouldn't have, but oh well. Yeah, well, I really hate giving it its own page. Let's actually not give it its own page because I noticed that it's going to be easy. So we'll go and put, wait, that was C. C, that's, oh, I skipped C. All right, well, in that case, we will give it its own page now, because we'll do D. Okay, so, shoot, you know what? Just for the sake of making these notes nice and precise, we're going to do it this way. We're going to do C, D, and E on the next page, I think. Yeah, let's just go ahead and do that. Yeah, I skipped old C there on accident. Okay, so let's try this again. So C, we have 1 over 25 raised to the 3 halves power. Okay, so 1 over 25 raised to the 3 halves power is the same thing as saying that we have the square root of 1 over 25. Oops, that's not it. The square root of 1 over 25 all raised to the 3rd power. Okay. Because again, that implied 2 gives me a square root. Well, what is the square root of 1 over 25? Well, that's just 1 over 5. And then 1 over 5 cubed, right? Well, that's just 1 cubed over 5 cubed, which is 1 over 125. Okay. And then D, we just did D. We're going to do it again. We're going to say 1 over 4 to the 3 halves. All right, we know that can be written as 1 over the square root of 4 cubed. Well, square root of 4 is 2. 2 cubed is 8, so 1 over 8. And then E, this is finally we're getting to E. All right, I see that we have a negative number. All right, it's a negative number that I cannot take away from that 81. We saw previously on C here that I was able to split up -1 and then the 100. I was able to split it up, but I was unable to split it up here, right? Or rather here. So I can't take the negative away from the 81, and it's being raised to a 3/4 power. The denominator there is an even number. So what I have to do here is I have to, I know that since it's an even number, it's going to be an even radical, and I cannot take an even root of a negative number. Right, so again, I cannot take an even root of a negative number, so that tells me I've got, my solution here is no real number. Well, there's not even an A there. Maybe something's not loading in right. I don't know. This is a little crazy. All right, so this reads, convert each expression to radical notation. Assume all variables represent positive real numbers. So A, I know I can, if I'm converting this to radical notation, the denominator there is 5, so it's going to be 5th root of A cubed. Right? Or alternatively, the 5th root of A and then all that cubed. B, right? So we have a 3 in the denominator of both of my numbers, right? I'm looking at B here. It's 5 to the 1/3 and x to the 2/3. So I know this is going to end up being the cube root of 5 and then x to the 2/3, which would be x squared. And C. All right, C and D are a little tricky, okay? Because the exponent is only on the variable. So we're going to write 3 times y raised to the 1/4. So if I have a 4 at 1/4, that means it's going to be the 4th root of y. Okay, let's fix that y just a little bit, of y. Right? And again, that's because the rational exponent is only attached to the y. Now D, we have a 9z raised to the negative 3/4 power. Okay, so since it is a negative 3/4 power, we can go ahead and kind of think of this as 9. Let's put D. Let's mark D down just a little bit further because we're going to have to make a fraction here. So we'll say 9 over z to the positive 3/4 power now, okay, because I changed it from the numerator to the denominator. So that can turn into 9 over the 4th root of z cubed. Okay. So there are a lot of rules that we have to remember from our review sections or previous math courses when dealing with our negative exponents and so forth. But once you start using them again, they come back. And for the record, this this concept that we're dealing with right now, I use it quite extensively, at least in Calculus 1. I mean, it's used a lot in the others as well, but especially Calculus 1, whenever you start talking about derivatives, it's really helpful and handy to understand how the exponents work. So this stuff that we're learning isn't just, let's say what I'm going to time wasters or busy work. It's not just busy work. Yeah, it is actually used in later math courses. And who knows, some among you might be taking that path to be a mathematician or an engineer or something like that. All right, so example 4. Convert each expression to an equivalent expression by using rational exponents. Assume all variables represent positive real numbers. So now we're going to be going the opposite way. So we're going to be going from exponents to radicals to exponents. So I see that for a, I have a 4th root. So the denominator of my rational exponent is going to be a 4. So it's going to be b raised to the, again, it's just 3's for some reason, 3/4. I mean, my 4's aren't much better, I know, but let's try it again. There we go. And then b, this is cool because b and c, they kind of look the same, okay? But obviously they're not. Spoiler alert. So we have 7. The square root of 7a. So both the 7 and the a are inside the radical. So both the 7 and the a are going to be raised to the 1/2 power. C is a little different because only the a only the a has the radical attached. Okay, so it's 7 times the a, which is the only one that's attached, or the only one that has the radical on it. So we'd say 7a to the 1/2 power. So B and C, a little tricky, but that's how that's done. Okay, so this deserves its own page. I wonder, because this is actually a little, let me see if I can, no, it doesn't fix anything. Okay, so I'm going to have to clean up the first one. All right, so this is the definitions and properties of exponents. So this, everything kind of looks okay. It just looks a little smushed. So let's actually move this over to the left and maybe correct some things over to the right. So property 1 is a to the m times a to the n. That's going to be equal to a to the m plus, crap. There we go. All right, so I try to clean this up. So let's start off here. We're going to be adding, subtracting, dividing, multiplying exponents. And these are the properties that we're going to be using to do all that. So if we let a and b be non-zero real numbers, let m and n be rational numbers such that a raised to the m power, a raised to the n power, and b raised to the m power are real numbers. So multiplying like bases. So like bases means that the base is the number that's being raised to the power. Okay, so I used base earlier, but that's what that means. It's the number being raised to some power. Okay, so if we have a raised to some n, a raised to some m times a raised to some n, then all we have is, then all we need to do is say a raised to the m plus n. Now, that's what I wrote over here because the m plus n got kind of cut off right there. And the example would be x raised to the 1/3 times x raised to the 4/3. Notice we have the same base, both bases being x's. So I can just simply add the exponents. 1/3 plus 4/3 is 5/3. If we're dividing like bases, then you subtract, right? A raised to the m divided by a raised to the n is just simply a to the a. Let's make that a little bigger. Oh, I can't make it too much bigger. There. I don't know if that helps or not. But then we subtract a raised to the m minus n. Sorry. The power rule is if we're raising a power to a power, then you multiply, right? If we have a to the m raised to the nth power, then we multiply. 1/3 times 1/2 is 1/6. Power of a product rule. Power of a product rule is kind of like the distributive property, but backwards, right? So notice we have uh, where are we at? Power rule. No, product. Sorry, power of product. I got lost. Sorry. So a times b raised to the m power. We basically just take the m, the exponent, and put it on both a and b. So we get a to the m, b to the m. Right. Power of a quotient operates kind of the same way. Yeah, honestly, the same way, except for the fact that instead of having a times b, we're having a divided by b. So a divided by b, a over b raised to the m power, is simply a over m, a over m over b over m. And then negative exponents, of course, we've talked about that. We've had problems like that before. If we have a negative exponent, then it goes from the numerator to the denominator, and then of course vice versa. And then a zero exponent is a to 0 is equal to 1. So anything raised to the 0th power is equal to 1. And real quick, before we do proceed here, just to really, I wouldn't say drive the point home, but just to really show why that is the case. Let's say that 1, okay, we know 1 is equal to anything over itself. So let's just say a over m over a over m. Okay. Again, that is equal to 1. It's the same thing over itself. Well, we know that from from number 2 here, dividing like bases, we end up with a to the m minus m, which is equal to a to the 0th power. And that's why anything raised to the 0th power is equal to 1. Okay, so now let's put these properties into motion here. Alright, so this reads, use the properties of exponents to simplify the expressions. Assume all variables represent positive real numbers. Okay, so A, we have y to the 2/5 times y to the 3/5. So we have a common base, right? A like base there being y, and we're multiplying them. Okay, well, we know if we multiply like bases, then we add the exponents. So we would say y to the 2/5 plus 3/5. That's awful. 2/5 plus 3/5. We're just going to have to live with that. All right, well, 2/5 plus 3/5, well, that's just equal to 5/5, which is 1. So we have 1. Alternatively, we've got b. Okay, so b has a 6 times a to the negative 1/2 divided by a to the 3/2. Alrighty, so there's a couple ways we can go about this. We could either move the a from the numerator to the denominator, or we could just go ahead and subtract them. All right, and we're just going to go ahead with the subtracting part. All right, since we have a like base, so we're going to say 6 times a to the negative 1/2 minus 3/2, right? Because since we're dividing, we can just simply shoot, 3 halves. Since we're dividing, we can simply just subtract the exponents. All right. Well, negative 1 half minus 3 halves, so that's going to be negative 2. So we're going to say 6, it's a big 6, 6a to the negative 2 power. Fix that negative 2 better. To negative 2 power. And then we know we can take that negative 2 power and put it in the denominator, so we end up with a 6 over a squared. And then C looks like a lot of work, but it's actually pretty darn easy. All right, and of course I say that, I know, sitting in my chair instead of yours. So let's go ahead and rewrite all this so I can really show you what we're doing here. Okay. So this was, I believe, called the power rule. So we're looking at, well, power of a product. We're going to look at power of a product here. Right? I said it's kind of like reverse distributing, right? And it's true. It is kind of like reverse distributing, because what we're going to do, we're going to take this 4 and we're going to basically distribute backwards, right? Reverse distribute through all of the exponents. Okay, so starting first, we're going to distribute it to the s to the 1 half. Well, that becomes, 1 half times 4 is 4 halves, which is 2. So we would say s squared. Distribute this again, right? So this becomes t to the 4/3, which just simplifies to t to the 4/3. Now let's fix that t. And then lastly, we would take this 4 and distribute it over here. So it would be 3/4 times 4, which would be 12/4, which is just simply 3. So w cubed. Okay, so like I said, it's it looked like a doozy, but it really wasn't. And then the last example, we've got example 6, applying rational exponents. So suppose P dollars in principal is invested in an account that earns interest annually. If after T years the investment grows to A dollars, then the annual rate of return R on the investment is given by R is equal to A over P raised to the, oh gosh, I can't even read that. Let's see if we can't make that a little larger here. By a little larger, I mean a lot larger. I guess that's, yeah, it's 1 over T. I should have just went by context clues, because I say it is because it says after T years, and obviously T isn't, you don't see, at first glance you don't see T anywhere in this formula, but it's the denominator of the rational exponent there. So let's start. If after T years the investment grows to $8, then the annual rate of return R on the investment is given by this formula. Find the annual rate of return on $5,000, which grew to $6,894.21 after 6 years. So it looks like we're trying to find A. No, we're not. I'm sorry. We're trying to find R. Okay. So R is going to be equal to our equation there. And before we begin, let's just do this. So we have R, which is what we are trying to find. Just write down the variables. A, which was 6894.21. P is equal to 5,000. That's my principal there. So 5,000. And then T is going to be 6. So T is equal to 6. Right? So all I have to do is plug in all these numbers. So I've got R is equal to $6,894.21 all over 5,000, right? And that's raised to the 1 over 6 power minus 1. Okay. This is going to require a calculator. So, and really quickly, while I'm at it, doing these rational exponents are really simple. Now you're gonna need a scientific calculator for this, but really simple because imagine if this problem was the sixth root of 68, and I'm just gonna write 694 to 5,000. 5,000. Okay, if you had the sixth root of something here. Now, your more expensive calculators, you can obviously put in the sixth root of something. There's nothing wrong with that, But however, I would never, ever suggest a student spend $150 on a calculator. It is absolutely ridiculous in this day and age that a calculator costs $150 when you can just download a free app on your phone. So instead of writing the sixth root of something, we're going to be doing what we've learned today and just putting into the calculator something raised to the 1/6 power. Okay, so give me one moment while I put this into the calculator. I really hate doing calculator work when I'm I mean, honestly, in class, but it's not terrible in the classroom. But when I'm especially on Zoom, or in this particular case, just simply YouTube, putting stuff into the calculator sucks because you can't see me. But anyways, so let's try this. Okay, so 6890 raised to the 1/6 power. Okay, so raising this to the 1/6 power and then subtracting 1, I get 0.05. It doesn't say necessarily how much, how many decimal places, but we're talking about percentages here, so we'll just go out 1. So we would say 5.5, right, which is going to be equal to a 5.5% if we put it in percentages. So the annual rate of return is 5.5%, which, I mean, isn't terrible. If it's a safe bet and you have a lot of money, it's not terrible. But if I've got $5,000, I guess I'd rather YOLO it on GME, right? I'm just kidding. Anyways, that concludes today's lecture.